Alright, this video is going to be called What the F Was That About? Um, Again, I have no idea how challenging or how completely foreign the mathematics that went into the fluid dynamics analysis, but at least let's talk about qualitatively, heuristically, what was going on. Before all that stuff, we did a derivation of the collapse time, the dynamic time it takes for it could take a spherical object, a spherical overdensity. What is the scale, the time scale over which that thing collapsed? That was this dynamic time. Okay, so let's think about this then. There are time scales. Time scales. And, I guess I should title this video, which is called What the Was That About? Handwriting is terrible. I.e., in other words, what is the gene's length? What is lambda j? What does that mean? Okay, and the way to get there is to think about there are two time scales involved. One is spherical overdensity. It's going to collapse. The time scale there was called the dynamic time scale, dynamical, and that was, if you recall, was equal to the 1 over the square root of 4 pi g rho bar, where rho bar was the average density in the background. Okay, there is a second time scale when you think about that there is a fluid that isn't just what you might call pressureless dust, but in fact there is some interaction between the particles causing pressure, and there is a pressure time scale determined by the size of the overdensity and the time that it would take a pressure wave to get from like the surface to the core. That would set the time over which it would take for the thing to start collapsing, and then all the particles that make up this fluid to sort of be able to talk to each other. You get the communication from the surface down to the core to say, hey, this thing's starting to collapse. Should we resist? Should the pressure act? Again, this is heuristic. That time scale I would call the pressure, the time scale of the pressure. I'll call it pressure. That is indicated by, or it's given by, the distance that the signal has to travel. That's more or less given by the size of that overdensity, which we'll just call r, the radius of that spherical overdensity. And then this is divided by the speed at which signals can propagate in a fluid with pressure. That, in other words, that is the sound speed. That's what a sound wave is. It's simply a disturbance in the pressure as it travels around. Oh, okay. So that's what we have. And if you think about it then, try to picture this, that you've got an object that can start to collapse, and if it can collapse over a time scale that is shorter than the time it takes for the pressure signal to get down to the core and back, then that would mean that the thing has an opportunity to collapse before pressure can act. In other words, you could say that if the time scale for collapse, in other words the dynamic time scale, if it's less than the time scale for pressure to act, then you get growth. I'll call this, maybe I'll call it collapse, or growth of structure, growth of some overdensity. And then on the other hand, if the dynamic time scale is longer, that is to say that the time it takes for this thing to collapse takes a long time, and in the process, let me add, this is much less than suppose. In the process, it takes a long time to get there, but in the time, there's plenty of time for the signal to get from the surface to the core and back to say, hey, this thing is collapsing. What should we do? Let's provide pressure. It's not quite how it works, but anyway, if that time is much longer than the time scale for pressure waves or information to be communicated in that medium, then we would say that you don't really get this collapse. Instead, you're just going to get pressure waves. You're going to get oscillations. So oscillations, or as a student of mine said several years ago, before I guess this person had ever read this word, oscillations. Yeah. Anyway, good. So that means that there is sort of a transition between these two behaviors, between just having structures collapse and having them undergo some kind of waves, oscillations, and that would be that when these time scales are more or less equal. So this is a kind of hand-wavy relationship. In other words, we could say when T dynamical is on the order of the scale of the time for pressure, then that's the transition. When this is in between. in between the transition. So let's just set these two things equal and see what we get. The dynamic time scale was 1 over the square root of 4 pi g rho bar. The pressure time scale was the size of the object, the size of the overdensity divided by the sound speed. And if we set them to just be equal to each other, we could ask, well, okay, what do we learn? The density of the fluid is just whatever it is. G is some number. The sound speed is given by the medium. What we're interested in solving is the critical radius at which, in other words, the size of the overdensities at which you get a transition from gravitational collapse to oscillations. When that occurs, what we're going to do is we're going to call this basically the Jeans length, or if you like, this would say that R would be given by CS times, or if you like, divided by square root of 4 pi g rho bar. This is the special, I'll call it the sort of Jeans, we'll call it the Jeans radius, if you like. Again, nothing to do with Levi's jeans, although that's a good joke you can make. That would set the scale. And this is more or less equal to what we actually found using the analysis from the previous video. If you actually did this with fluids, then you would find that the Jeans length is given by CS, and then at least I don't remember where my notes are, maybe they're here. I think it was a square root of pi divided by g rho bar. So you can see that clearly the order of magnitude is comparable. The scale is set by the sound speed and g and rho bar. And again, the whole point was that for radii, or distances for overdensities, perturbations smaller than this length, in other words, for lambdas less than lambda j, the Jeans length, all you get are oscillations. More or less, you've got pressure causing an oscillation between over and under dense, and on top of that, yeah, there's some gravity that's kind of pulling it perhaps a little bit tighter, but they're oscillations nevertheless. For perturbations that are bigger than the Jeans length, then you get growth. You get gravitational collapse. You could also call it perturbation growth. The density perturbation grows. Right. So hopefully that provides a little bit more physical intuition for what all that stuff was about. We should say, I will say, that for a general fluid, so in general, for general fluid, and that would be a fluid in which there is an equation of state parameter that relates the energy density to the mass density. For general fluid, the speed of sound is equal to the square root of W, that equation of state parameter, times the speed of light, c. And I'll just sort of remind you, W came in when we had a simple linear relationship between the pressure and the energy density of some substance. Then W would be the proportionality factor. For a highly relativistic plasma, remember what we had found for photons. So highly relativistic plasma, the equation of state parameter W was 1/3. And so what that means is that the speed of sound that you would get would be, 1 over the square root of 3 times c. So actually still quite fast. Not quite the speed of light, but if you had a highly relativistic plasma, then sound waves would travel, just about, roughly half the speed of light. So it's still pretty fast. Okay, so let's think about this then. So let's analyze what happens with with this general fluid. Remember what I just wrote up above, that lambda j is given by the sound speed times square root of pi over g rho. Okay, what that means is that in general that's the square root of W times the speed of light times the square root of pi over g rho. This may or may not look familiar to you. Perhaps what I could do is you can imagine that the relativistic version of this is to take the density, the mass density, and replace this with its relativistic expression, which would not be in terms of just a mass density, but in general, this would be an energy density, right? We're thinking about Einstein, the E equals mc squared. So what that means is that the energy density is equal to the mass density times c squared. So if we make that substitution, if we replace the mass density with the energy density divided by c squared, this can be written as square root of W, c, and then pi, there's a c squared on top, a g, and then this is epsilon bar, the energy density average. And hopefully this combination of things, with any luck, it will look familiar to you, but it may not. So let me just remind you, we've seen that combination of things show up before in a slightly different form. The Friedmann equation says Hubble parameter squared is equal to, in a universe in which there's just one component, this would be 8 pi g over 3c squared times the average energy density. Okay, so what that means is that's very similar to what we have. In other words, just for comparison's sake, if we take the square root of this, take the inverse of it, the inverse of the Hubble constant, that is equal to the square root of 3c squared over 8 pi g epsilon bar. And so you can see, although there are some numerical factors there that are different, notice the c, whoopsies, my trick, c squared, the epsilon bar, and the g. That's what you can identify here, and that's indicative that we that means that the gene's length is somehow related to h inverse. So let's go a bit further and just figure out what happens when you multiply lambda j, the gene's length, times the Hubble constant. Well, that would be the square root of wc square root pi c squared g epsilon bar times 3, times, actually I mean the inverse of that, 8 pi g epsilon bar over 3 c squared, and a bunch of things cancel, and I claim that if you do this carefully, you will find that this cleans up quite a bit to 2 square root of 2 over 3, there's a pi, and a square root of w, and a c. More or less. Okay, good. What does that mean? The gene's length can be written in terms of 2 pi square root 2 over 3 square root of w c h inverse. And if you work out these numbers for a highly relativistic fluid, but highly, well, yeah. So I'll just say relativistic plasma, which is what we've got in the universe until basically after decoupling. At least photons and barons make a highly relativistic plasma. Relativistic plasma in which W is basically equal to 1/3. And that means that this is approximately 2.96, I have computed, times C H inverse. In other words, the gene's length, the length below which you don't get structure formation, is about 3 times the Hubble length, which is basically like the size of the universe. What all that means is you need to have a the matter component, the stuff that turns into us. We need to have something, a lambda j, much less than the Hubble length in order for there to be meaningful structure growth on scales smaller than the size of the observable universe. And the trouble is basically that this does not occur until the baryons decouple from photons at the time of the CMB formation.